Welcome. I thought I would start this first session, and actually my first time ever teaching a class using Blackboard Collaborate, by talking about something from Chapter 1 and showing you some examples from things in Chapter 1, and that's unit conversion. Now, unit conversion, you might think that seems kind of boring, but actually having a standard set of units and figuring out that everybody's using the same set of units, that's really important in a lot of areas. Business, for example, if you're going somewhere and you're trading grain, if you've got a unit of grain and some other nation has a unit of currency, and they're thinking they're getting a certain size unit from their point of view, but you're giving them a unit that's maybe twice that size, and they're paying you a certain amount of money, then you are losing money because you're giving them twice as much grain as what you think you would be giving them. So standardizing units and figuring out how to convert from one unit to the other. So your unit of grain is one thing, their unit of grain is something else. So you measure by the kilogram, they measure by the pound. They think they're buying a pound, but you give them a kilogram. Like I said, you've lost roughly half of your profit because a kilogram on the surface of the earth is roughly twice the weight of a pound. So when you do unit conversions, there are a couple things to remember. And really, so when you're doing it, definitely you want to start with whatever the original units are. So if you're converting, let's just convert something, you're in your car and you're in the United States, but then you go to Canada, and in Canada they have a different set of units. So let's say that your car, you say that you are going 70 miles per hour. And I apologize, my child is printing here. It'll definitely improve as the quarter goes on. And you want to know what that is in meters per second. So this is what you wanted to know, the miles per hour. You want to go to meters per second. Unit conversion really is just multiplying by 1 any number of times that you need to get to the proper units. So for example, 70 miles per hour. And let's say we want meters per second. All right, Khan does this printing a lot better in his Khan Academy videos. Anyway, so we want to get to meters, we want to get to seconds. So miles and hours. I don't really know right offhand, maybe I can't remember the miles to meter conversion. So what I like to do is set up a parenthesis like this, set up the dividing line, I forget what the official math name of this is, and then canceling things out. So hours is on the bottom here, so I need it to be on the top right here. And let's say maybe I don't know the number of seconds in an hour, but I know the number of minutes in an hour. I know that there are 60 minutes in 1 hour. Well, I've canceled hours, but I don't know what that is now. That's miles per minute, but we want meters per second, so we're still a ways away. So we need to do this again. So now we want to cancel minutes. Minutes is on the bottom. We want to get rid of that, so we need minutes on the top here and seconds on the bottom. Of course, mathematicians call this the numerator and the denominator. So I know that 1 minute is 60 seconds. So now I've canceled minutes. Now I have miles per second. And since I'm running out of space here, I'll do this last conversion in one step. I don't want miles on the top, so I put miles on the bottom and then meters on the top. And I happen to know that 1 mile, well, I might be off by 1 or 2 meters. I believe it's 1609. Those of you who do track probably know that. You either know that that's correct or you know that that's incorrect. All right, Brittany has joined. She is actually in the chat window, so she must not have a microphone. So Brittany, if you do have a microphone, you can use that. Otherwise, you can just type things into the chat window. And if your chat window starts off really tiny, you can actually disengage it from the main window and slide it over to a different part of your screen if you have a big enough screen. So if you need to type something in, you can just say whatever you want. You can use an emoticon. Since this is physics class, of course, you'll only want to use happy emoticons. Anyway, we've canceled the miles, and now what we have left here, and this is going to, let's see, I can use a different color. Now we have meters, and we have seconds. Oopsie. We've got to get rid of that. So I'm using this little pen that replaces the mouse for the first time. So we've got meters on the top, seconds on the bottom. And then if we multiply these out, and I'm still trying to get the feng shui of my space here. So I'm not even sure where I put my calculator. Let's just go to the web calculator, which you won't be able to see on your screen. But that's okay, you can figure that out anyway. So 70 times 1609 divided by 60 divided by 60 equals, that I do not think is correct. So if you've been listening along, you know whether I did that right. So let's see here. Try this again. 70 times 1609 divided by, there we go. I missed a factor of 10 before when first time I did it on my calculator, or the computer's calculator. So that comes out to be equal to 31.3 meters per second. And actually, if you do go up to Canada, I think they have their signs in kilometers per hour, so they wouldn't be in meters per second. Meters per second is the standard unit of speed here. So meters, that's the standard length unit. And seconds is, I probably should say is rather than equals, the standard time unit. And notice that I actually was canceling out the units as I go along. So I was left with the meters up here and the seconds down here. So Brittany, have you done unit conversion before? And looks like you don't have the microphone, but certainly you can type something into the chat box.
Yeah, I've done unit conversions before.
Okay. So maybe you can, let's see, let's go to the next one here. So I'll go through this one again. So this is pretty much just a review. Actually, Brittany, why don't you work through this one, and then once you do it, I'll work through it. You can work through it not looking at the screen, and then we'll see if we match. So I'm gonna write on the screen, but I won't say anything. So Brittany, what'd you get for an answer?
Hold on, I'm still calculating.
Oh, okay, no problem.
I got 1,231.2.
Yep, that's what I got too. So with significant digits, if we assume that all these are significant, and chemistry, they are really big on significant digits. I'm not that excited about them. And it sort of depends on what precision you need. So in chemistry, if you're doing something and you're just going to be extracting 1 gram of substrate out of a couple kilograms of 2 solutions mixed together, then it really is important because 1 gram out of a couple kilograms, that's a tiny number. So for this, if we want to be precise, 342, so I got the same thing that Brittany did, but I would then round off. So let me write everything. So I'll definitely respect her answer. So 1231.2, and I'm not just going to put that. Even though it said, what is this in kilometers per hour, strictly speaking, simply writing this number would have answered the question, but it's always a good habit to do that, to put the units as well. So for 3 significant figures, sometimes called sig figs, you could also write this, kilometers per hour. The problem with doing it this way specifically is you don't know whether this 0 is significant or not. It could have been that the answer, we know if we calculate this, that it's what I have circled. Is this a circle? It's what I have kidney beaned here. So the better way to do this is to write it in scientific notation. So scientific notation would be 1.23. I know this doesn't look very much like a 1, does it? Looks like an unfolded paper clip, times 10 to the, and we had it here. Actually, let me use a different color. So we're moving it over 1, 2, 3 spots. And I think you can memorize the rule. You're moving it to the left, it's positive, right is negative, or whatever. I can never remember the rule. In fact, I probably said it wrong. But I know that since I have a number larger than 1, this has to be positive. I'm not big on memorizing rules because oftentimes rules are set up along a certain situation. So with trigonometry, we'll deal with this later in the quarter. Some people like to memorize, oh, if it's an angle measured with respect to the x-axis, it's one trigonometric sign. With respect to the y-axis, it's another. But it really depends on a lot of different things. So I like to just look at the picture and say, oh, this must be sine or this must be cosine. Same thing here. I don't want to memorize left or right. So I started with the decimal point here and I moved it to the left. But what if I said, oh, I know it's got to be 1.2. Which way do I have to move it to get to the original number? Well, then I'm moving it to the right. So which rule am I remembering? But anyway, this tells me now that I have 3 significant figures because I've got 3 figures right there. So the significant figure thing isn't important. Probably the sort of my parenthetical thought about the scientific notation here is even more important in knowing whether it's positive or negative. So if you've got a number that's larger than 10, you are going to be having a positive number here. If this would have been 0.00123, then this would have been negative right there. Another interesting fact. So these are, by the way, you probably figured this out, problems from the book, problems 8, 9, and 10 in chapter 1. Picking them to kind of start the quarter off slowly and also to give myself practice on something fairly straightforward using my pen here. So tectonic plates, they have an average speed of 4 centimeters per year. So I also kind of like to look at problems that have interesting trivial facts as well. So 4 centimeters per year. That's 4 centimeters is, if you have a really small hand, probably about the width of your hand, but for most of us regular sized hands, 4 centimeters is less than the width of your hand. But to the ancient people, they would have been impressed that they're moving at all, because they would have thought the earth, many people would have thought the earth didn't move in the heavens, and the plates didn't move. You know, they wouldn't have even known what plates are. So if it moves 4 centimeters per year, what distance does it move in 1 second? So I'll go back to black again. And maybe Brittany has worked ahead on this. If you have, that's great. And then we can match answers and see if that works out. So 4.0, and the fact that it's 4.0, that implies 2 significant figures. So you've got a ruler here that measures in centimeters. Probably 4.0 would actually be, you could estimate if you just had a ruler that only had centimeter lines, you can do a pretty good job estimating to the 10th. So 4.0 centimeters per year. And we want to know, what does it move in 1 second? So this means we get to keep the centimeters, and now we're just going year. Maybe some of you know how many seconds are in a year. I never remember that. So let's just go the long way. So 1 year, so we for sure know the months. So we know that 1 year is 12 months. So we can cancel out the year. We know that 1 month, oh, how many days should we use for that? Because months have different amounts of days. Oh, I wonder what the average is, a little bit over 30. Let's just use 30 days. And actually to 2 significant digits, that is probably close enough. So now we've canceled out the months. Now we have centimeters per day. We don't want centimeters per day. We want centimeters per second. So we know that 1 day is, I don't even know how many seconds are in a day, although I could probably quickly do it in my head, but I definitely know days to hours, and that's 24. Again, it's not exactly 24, but that is certainly close enough to 2 significant digits. So we've canceled the days, and now we've got hours to seconds, and we remember from earlier 3,600 seconds is 1 hour. So now we've got seconds. We haven't even touched the centimeters. So we've got centimeters, and then we can figure out what the answer is. And I'll need to do that on my calculator over here. So let's see, 4 times, oh, now all 1's at the top, so that was kind of silly of me. So when I was in college, I had a chemistry partner who would always multiply by 1, because you know you're doing these calculations. I'd say, well, why do you have to multiply by 1? It's not going to change it. And she said, you never know. So she was expecting one of those times to multiply by 1 and get a different answer. So when I plug this in, the calculator on my computer gives it to me in scientific notation. So 1.29 I get. So to 2 significant digits, 1.3 times 10 to the minus 7th centimeters per second. So that'd be 10 to the minus 9 meters per second. So that is a very small rate of speed. So what is the speed in kilometers per million years? So we can go to kilometers. Smarter people watching this perhaps can go right from centimeters to kilometers. I'm going to go to meters as an intermediate, feel free, if you can do it quickly, go right from centimeters to meters. And I also like to do it where I use numbers that are bigger than 1. So I like to say that, so by the way, I'm just canceling out centimeters. I like to say that 1 meter is 100 centimeters. Some people might say, okay, 1 centimeter is 1/100th of a meter, but this makes a little bit more sense to me. You're less likely to goof up, I think, with whole numbers rather than with decimals or certainly with fractions. And now meters to kilometers. So I know that 1 kilometer, that's the bigger one, is 1,000 meters. And you can see right off the bat I could have gone from centimeters to kilometers because that would then be 100,000 centimeters is 1 kilometer. And for this one, I don't even need my calculator. I can go 1.3 times 10 to the, I'm going to do a few steps here, so -7. And if I take that one and then that one, so -7, so 1 over 100, that's 10 to the -2, so I can do -2 here. 1 over 1,000, that's 10 to the -3, so -3 here. Sorry for spreading that all out. And I should have circled this when I had the red color. Here we've got kilometers per second. And I know that's not what we want yet, but I will definitely get to that. So kilometers per second. So that's 1.3 times 10 to the minus. So -7 minus 2 is -9. -3 is -12 kilometers per second. But now, what is the speed in kilometers per million years? So I kind of ran out of space here. I'm going to go to years on a separate one. So if we do this, 1.3 times 10 to the -12th kilometers. Oops, sorry. I'll see if I can remember how to erase this. All right, that's some proficiency right there. So kilometers per second. Sorry, I just patted myself on the back. So now we can go seconds to year, because what we did up here is we actually did the conversion. I didn't actually do the math behind it. What's a good, here's a color I haven't used that looks different. That's kind of ugly. Let's go this sort of greenish color, is not too bad. So I did this calculation right here. So I'm actually not drunk when I do this. I'm writing on this little pad and I need to look at the screen because I don't see what is actually being written on the pad. So we could figure this out here, and so that's going to be, and so we can actually figure out what the conversion is. So 1 divided by 12 and all those other things right there. So it turns out that the number of, and I actually did it backwards, so I went against, oh wait, maybe I can invert that. There we go. So I now know that there are, oops, I don't want that. Let's go with black again. So I just did this on the calculator. There are 31 million seconds in a year. So 1, 2, 3, 4, 5, 6. Wait, that's not right. 1, 2, 3, 4, 5, 6, 7. So there's 3.1 times 10 to the 7th seconds in 1 year, so we've canceled out the seconds. So now we know kilometers per year, but we want to know kilometers per million years. So kilometers per million years, it's kind of an odd conversion. And to tell you the truth, I had to actually think about this myself. Remember, unit conversions are always multiplying through by 1. So right here, for example, I'll use a different color. So right here, 1 year equals 12 months. So if something divided by itself is equal to 1, 6 divided by 6 is equal to 1. 1 year is 12 months. 1 month is 30 days. I know that's not super precise, but you get the idea. 1 day is 24 hours. So everything in these parentheses here, you're really just multiplying by 1. And you're multiplying by 1 strategically, because if you just multiply by 1, that doesn't make any sense. So you're strategically multiplying by 1. So in this case, the seconds cancel each other out. And this one, if some of you might be really good at multiplying things together. So what I would do for this, I would multiply 1.3 times 3.1. And that gives me, sorry, I'm going one step too quickly here because I forgot the million years thing. I went off track. So we want it per million years, so I'm just going to multiply by 1 again, which is a million over a million. But in the bottom, in the denominator, we're going to leave it as million years. On this pen here, when I push a certain button, it goes to the little box that allows me to delete. So every so often you'll see that box appear. And we're left with kilometers up here. So now 1.3 times 3.1 is 4.0. And I think I squished it. I didn't squish it quite this much. So now we've got negative 12 plus 7, so that's negative 5, plus, and this I probably could have left it as a power here, so that's 1, 2, 3, 4, 5, 6. So I guess that's good. I'll use this space. That's negative 12 plus 7 plus 6, or 4.0 times 10 to the, what's that going to be? It's 10, right? 12 minus 7 is negative 5, plus 6 is 1. So 40 kilometers per million years. And again, I got so excited I got the answer, filled it in the box, that my writing went all to heck. So by this estimation then, it turns out the plates move about 40 kilometers per million years. So 40 kilometers, let's see, that is roughly 25 miles. So about the distance between Ellensburg and Cle Elum. Or what would that be? Maybe the distance between Kent and downtown Seattle, or Auburn probably in downtown Seattle. So that's how much the plates move on average every million years. So the last one here, refer to this certain table, but I actually just gave you the number. And Brittany's the only one actually who's listening to and watching this live. She was in astronomy this summer, so of course I would not have had to tell her the average Earth-Sun distance. She may not have remembered this number, because I have to think a little bit about this number. But if you've ever heard the term astronomical unit, the astronomical unit is the average Earth-Sun distance. So you might remember that as 93 million miles in kilometers to 2 significant digits, actually to 3 significant digits, 1.50 times 10 to the 11th meters. And the distance between the Earth and the Sun varies by roughly 3%, I think, a year. So it's not always this. This is the average distance. And 2 days a year, it is this distance. So what's the average speed of the Earth in kilometers per second? So how do we figure that out? So Brittany, any ideas on that? You can either say them or type it into the chat window.
I don't know, hold on.
Okay. Because this is a unit conversion, but there's actually a formula, actually a couple formulas that sneak in here as well.
So we'd have to take into consideration the distance that it's going to travel, or,
So if I were to draw a picture, what sort of picture would I draw? What would I have in my picture?
The Earth, the Sun, and the Earth's orbit.
Okay, so yeah, good. So we've got the Sun, we've got the Earth, and we've got the orbit. I'll just pick one of my colors that I've used before. So now I realize I should actually pick out a color palette beforehand. Otherwise, I'm faced with this decision of lots of different colors. Yeah, so we've got that. And this is where the Earth avoids some alien spacecraft, I think. Not sure what happened on that one. I think my wrist slid off my little pad here. But anyway, this distance, let me use a different color. So this distance here is the one astronomical unit from here to here, the average Earth-Sun distance. So yeah, now it's going in a circle. So it's not just a straight line. Average speed. So what's the formula for speed? Right, and so one other person has joined. Juliana has joined. Looks like she's lagging a little bit. Oh, that's insulting. Her microphone is lagging. I'm getting some symbols here that there's a little bit of slowdown. And Juliana, you have your camera on. You can actually, if you shut that off, you might get quicker response time. You might not get such a lag. And actually, I'm going to block cameras from folks. So it's the speed. This is a basic formula. Starting with chapter 2, we'll talk about velocity, which is something a little bit different from speed. You can actually define speed in a couple different ways, but the most basic version of speed is distance traveled. Oopsie. Distance traveled divided by the time taken. So the speed in this case so the time taken, that's pretty easy. So the average speed of the Earth in kilometers per second. So there's definitely one unit of time that we know about, and that's a year. So I don't know how precise we want to be on this. I happen to remember that a year, very, very close to 365 days, but very, very close to 365 and a quarter days. So that's a time unit. And then the distance traveled. So we need to know what this distance is right there. So if you're super knowledgeable about astronomy, I actually drew my circle backwards from how you'd normally do it. This is how the Earth as viewed from above, so looking down from the Earth's North Pole, the Earth goes around the Sun counterclockwise. I do a clockwise circle. That would be how it would appear from a spaceship that's well below, so looking up from the Earth's South Pole. So this circle here is the circumference, or what I drew, this blue arrow here is the circumference of the circle. So the distance traveled is going to be the circumference. I gave you the radius. In red here, this is the radius. So we know that's going to be 2 pi times the radius, or 2 pi times the distance traveled, which is 1.5 times 10 to the 11th meters, divided by 365.25 days. So we now have it in meters per day. If we wanted to then convert to kilometers per second, so we need to go from meters to kilometers. And actually, I'm going to undo what I just did there. I'm going to try to use my fancy pen to do it, because I always do it accidentally. There we go. I'm very proud of that. So I'm just going to multiply by the units here, and we'll just acknowledge that I kind of stretched it. So from here to here, because I don't have any more room over on this. That wasn't very good planning. So I want to go meters to kilometers. So I know that 1 kilometer is 1,000 meters. And then I want to go, it says seconds to day. So I want to go here. So I want seconds on the bottom and day on the top. And actually, let me not do that, because we haven't actually figured out, I don't think, seconds per day yet. So let's get rid of some of these stray marks here. So I'm going to go seconds per hour, and that's 3,600 seconds per 1 hour. And then we'll go, so seconds has, so hours has canceled. And now we need, we need to cancel hours, sorry, hours per day. So now I've canceled days on the top with days on the bottom here, meters on the top with meters on the bottom here. And I've canceled out the hours. So I'm ending up with just the units that we want, hopefully, seconds per kilometer. So if you do this crossing off, you certainly don't have to do that all the time, but doing this crossing off, at least when you start, really helps you keep track of things. And in a lot of physics problems, you're going to be converting from one unit to the other. But of course, I didn't write these down yet. So this one day has 24 hours. So we're going to multiply 2 times pi times 1.5 times 10 to the 11th times, well, 1. So my college chemistry partner would have multiplied through by all these ones. You don't have to enter those in your calculator. but 2 times pi times 1.5 times 10 to the 11th on the top, and then on the bottom, 365.25 times 1,000 times 3,600 times 24. And if you multiply all that out, you get, and just to quickly check it out here, you could actually do a little bit of an estimation. So let's estimate. So 2 times pi is 6. Let's just go powers of 10. So 6 is the closest power of 10 is 10, so 1. So we've got 10 to the first times 10 to the 11th. So we've got 10 to the 12th on top. On the bottom, 365, that's closer to 100 than 1,000. So that's 10 to the second. This is 10 to the third, so now we're at 10 to the fifth. This is, again, 10 to the third, so 10 to the fifth times 10 to the third. That's 10 to the eighth. Here we've got 10 to the ninth. So we had 10 to the 12th on top, 10 to the ninth on the bottom. So we're going to be ending up with a number that's about 100 or 1,000. It turns out that since we underestimated all these so drastically, we come up with a number here that is closest to 10 to the first, so 20 kilometers per second. And I actually didn't do this beforehand. I'm looking at the answer in the book, so you see me looking down. And you can determine if that is right here. So I think I did everything right. So my estimation was actually, my power of 10 estimation was a little bit off. So what is this in meters per second? So we can just immediately do the calculation here to meters per second. So kilometers to meters. So 1,000 meters, is 1 kilometer. So that's going to equal 2.0 times 10 to the fourth meters per second. So that's all I wanted to say about practice. Let me just give you a few tips for success in physics in general, but certainly in this class where you're going to be using the Expert TA. So even though you're doing your homework online, you might think, well, since I'm going to be entering my answers online, I can be sort of scattered in how I do things and just write things on different parts of the paper. But no, you definitely want to be orderly. So even with my unit conversion problems here, so a unit conversion problem, you might scoff at the fact that this is orderly, but I had really 3 rules. Start with the number that I know, multiply through by 1 successively, and then cross things off as need be. So this is still pretty orderly. So if I do this and I enter this number in Expert TA and it tells me that I'm incorrect, and Expert TA gives pretty good feedback, actually gives very good feedback for an automated system. If I would have entered 4.0 times 10 to the 2, it would have told me to check my powers of 10. So if I go back here and I know, oh, okay, I've got to check my powers of 10, I would look and I'd say to myself, oh, shoot, when I wrote this down, I accidentally wrote down 10 to the 6th here. Actually, I wrote down 10 to the 8th. If I would have put 10 squared here, I'm off by too much. So I would have said, oh, look, I wrote 10 to the 8th here. That's why I got too big of an answer right here. Then I'd go back and I'd enter 4 times 10 to the 1st, and I'd get it right. So the fact that even though I'm entering it online and nobody's really checking my paper, doing it orderly like this really helps. So do each step on paper. Keep a well-organized problem notebook. Again, since you're not submitting a notebook, you're not submitting written problems, you might think, oh, I don't really need to keep it in a neat notebook. But here's a place where doing the homework online can actually be better, help you be better organized than submitting a notebook. or submitting homework on paper. Because if you submitted the homework on paper, what you'd do is you'd tear a piece of paper out of your notebook, or you'd undo it from your 3-ring binder, you'd give it back to me, and it would then be separate from your notebook. It would be up to you to then put it back in your notebook. If you just keep a notebook always and you're not tearing anything out, that helps you be better organized. And then if you have any questions about a problem, if you're keeping it in a notebook, you can write the question next to that which you are having a concern with. So let's just say right here, I'll go with a different color. Let's go with, no, not a drastically different color, kind of this orangish color here. So let's say I wasn't very sure about this. You know, maybe I don't remember, maybe I'm unsure, and I think, and I ask myself, is this 2 pi r or pi r squared? Now I committed to 2 pi r right away and I knew that was the right answer. But let's say I wasn't sure, I might leave myself a note here. And then afterwards I might go back, and when I figured it out, we'll use a different color. I'll use possibly one of the ugliest colors on here. I might again correct myself and say, oh, this is actually the area of a circle. So now I've made note of a question, I've thought about something, and by writing this down that this is an area of a circle, in a future problem where I need to know the area of a circle, I'm slightly more likely to remember it because there was a time when I was confused, circumference versus area. Not the concept, but the formula. So I could go back to this, and maybe I even remembered it was this problem, because the problems that you do earlier in the quarter, especially if you're new to physics and you're feeling a little bit uncomfortable, these first problems, getting in good habits early, you're going to really remember that. So any questions? You can verbalize your question, or you can enter the question into the chat area. In fact, just to remind you of that. And also, if you have any comments just on how this went, even though I was scribbling, that printing should hopefully get better. But if you have questions, comments, or suggestions on how to better organize things, this is going to be my standard organizational scheme. I'll make most of these sessions problem-solving based, because sharing facts, the book gives you facts. So if I know that there will be some concept that people have trouble with, I'll go over that. But I'll usually go over things kind of in the context of solving a problem, going through something step by step. I won't lecture and just read off a bunch of facts to you. If there's some diagrams in the book that I think are confusing, I'll put the diagram on this white screen and then I'll write. So most of what you see during these sessions will be primarily white screen to begin with either a problem or a diagram. If you have questions that you want to ask me, certainly you can ask them at the time. If there's a problem that you'd like me to go over, I would actually prefer that you give me that beforehand, because during the whole online Blackboard Collaborate trying to write, oh, and by the way, yeah, so just looks like a pen, but I write on this pen, and some of you may have something like this. There's this tablet here, and it's connected to where the mouse plugs in. So I just write on this thing here, and that's how it goes on the screen. But I know that if you ask for some super difficult problem, then I'll be trying to figure out how to do it on the tablet and then trying to solve the problem as well. And not that I won't try. If you think of a problem right at the time, of course I'll go over it. but it probably won't be quite as fluid. But if you say in advance, I'd like you to go over a certain problem. If it's on an upcoming homework assignment, I won't go all the way through to the answer, but I'll definitely help you set it up. So Juliana asked, will all of these sessions be recorded for students who can't attend? And yes, they will be. So all of the scheduled sessions that have names like Introduction to Physics or Introduction to Kinematics or explaining graphing, if it has a specific title like that, it will be recorded. You'll notice that there's a session, I don't even remember what it says right now, but it's actually, I can go to that. It says something fairly generic. It says unscheduled office hours meeting room. So those won't be recorded. That would be for a time if you just have a question, you say, I'd like you to go over a problem with me, and then we could set up a time. Of course, a lot of you can just come into the office, and that's fine as well. But if you want to do it in this way, where you can write something on the whiteboard, so you might notice that you also have access to the whiteboard where the participants are listed, right above that, and actually I suggested that you look to this. So this is the interface that you see, and I put a couple helpful links on Canvas. One is to a video that shows you how to participate, and then a link to this 2-page document. This is just copy and pasted from that. So right here, that's the ugly color. Let's go back to black. So right here it lists all the things that are available to you. So in this little sample, students can use all of them. But this is the whiteboard. So in a more interactive session, you can write on a whiteboard as well, so I can see what you do. You'll probably have a little bit harder time because you probably just have a mouse. If you have a tablet that you can write on, then that works really well. And in fact, that would work better than what I'm doing right now. But yeah, all these titled sessions will be recorded. And you can access the recordings the same place that you access the session itself. Oops. My typing skills are pretty poor even if I'm not doing the other stuff. All right, so any other questions, content related? Again, you've probably practiced unit conversion before, but this at least gives you a sense for what these sessions will be like. And it's good to rehearse things as well. So those are the tips for success. And that was our last sample problem. Okay, well, I'm going to stop the recording now. If either of the two students who've joined in want to put something in the chat window, I'll certainly see it. Or if you want to talk, I'll certainly hear it. But I'm going to stop the recording. So that means after the recording, and you'll be able to see that I've stopped the recording too. And you might get an audible cue. But that means you can say bad words after the recording stops.